Alright, welcome back folks. So today we'll be looking at an example of a field, and that will be the set of rational numbers. So I'll start off by defining what the set of rational number is. Rational numbers are basically fractions, that is numbers of the form p by q, where p and q themselves are integers, and usually this would be the end of it, but I'll be adding some more constraints, which is that GCD of P and Q is 1, that is P and Q don't have a common divisor, so this P by Q is in its lowest fractional form, and Q is obviously not 0 because you cannot divide any integer by 0. Okay, so this is the definition, but I'll be adding some additional structure over here. So take this for granted that if there is a fraction P by Q, if you multiply the numerator and the denominator by an integer k, then that won't change the value of the fraction. So these two rationals are equivalent, and this is valid for any k that is not 0. Okay, now I have defined the collection of numbers. The second thing is defining the addition operation. The addition operation is p by q plus r by s. These are two rationals. If you add them, it will result in p times s plus q times r over q times s. Now notice that the addition and the plus and the multiplication in the numerator and the denominator is the integer multiplication and addition. Okay, and similarly we can define the multiplication of two rationals as p by q over r by s is p times r over q times s. Now notice that q and s by definition are non-zero, and hence q times s in both these cases will also be non-zero. And because of that, since the numerator and the denominator both are integers by definition, then obviously the whole fraction, that is the result of addition and multiplication, they'll also be integers. They'll also be rationals. And that's what the first property is all about, that is closure. The rationals under this sort of addition and multiplication is closed, meaning that if you add any two rationals together, you will get another rational. Similarly, if you multiply any two rationals, you will get another rational. And that's what I have just explained, and that's the proof of the closure property. Now moving on to commutativity, this uses the commutativity of integer multiplication and addition as well. So by definition, this p by q plus r by s, which are two arbitrary rational numbers I've chosen, they look like this. Okay, so another thing I forgot to mention is that generally this p by q and r by s, they are in their lowest forms, and the ps plus qr over qs, this is not always in its lowest form. It's not necessary that if you do it like this, it will be in its lowest form. So while adding fractions, remember that you crisscross, add, and then multiply the denominators, but along with that you also reduce it to its lowest form by finding out the GCD of the numerator and the denominator. But in this case I haven't bothered with dividing by the GCD, because I have already mentioned that those two, this fraction and the one that you get by dividing with the GCD, are both equivalent. Alright, okay. So moving on to the commutativity, again I have defined p over q plus r over s as this. I haven't bothered with the division by the GCD. Now notice that I can swap the order of qr and ps added together, and similarly in both the multiplications as well, I can swap the order of the operands in that as well. And down here I have just qs is the same as sq. Again, commutativity of addition and multiplication of integers. Now notice that by definition this can be decomposed into r by s plus p by q. Similarly, I have also written down the commutativity for the multiplication of rationals. Now moving on to associativity, this is a bit tedious, but please bear with me. let's start with something simple. Look at this. Now this part in the parentheses can be added up and written as this. This is by the definition of rational addition. And now applying the same definition of addition again, it will become this as the numerator and over here this as the denominator. Now, now the next thing I'll do is subtle algebraic manipulations. So in general, whenever I add two rationals, this parenthesis is also there, but by associativity of the integer addition, I can move the parentheses here, evaluate this first, and add it to that later. Now, if I evaluate this first and then split the integers, then obviously it can be split into this. So you will find that I have excluded the y1 y2 term, but that's because I can cancel these two terms over here because they are common to the numerator and the denominator, and that's by the equivalency of rationals. Similarly over here, the y3 term will come out and only a y1 y2 term will remain in the denominator. Again, the equivalency of rationals invoked. And now look at this term. This has beautifully come out to be x1 over y1 plus x2 over y2, and hence I have proved that rational numbers are associative in nature, at least in terms of addition. And similarly, by they are also associative in terms of multiplication, because, well, that's what I have written over here. I urge you to go through it yourself, write down the parentheses and prove it yourself as well. Again, as I mentioned before, please don't just listen to me, go through the proofs yourself. That will help you much more compared to just listening. Alright, now consider the identities. The first of which is the 0, that is the additive identity. In the rationals, the 0 is basically the integer 0 divided by the integer 1. Now, obviously, you can verify for yourself that p by q, that is any arbitrary rational that I have chosen, added with this rational 0 will result in itself only. And similarly, the rational 1 is the fraction integer 1 upon another integer 1. So multiply that with any rational p by q of your choice, and you will notice that it results in the same again. Okay, now this is where we have to get a bit creative. How will we define the inverses? How will we find the inverse? Now for the additive inverse, look at this. If we just use the negation of the numerator, then that will result in minus p by q. So there is no change in the fraction except that the numerator has been negatively inverted, and so you will get minus p over q. Now add these two together, it should result in 0 over q. Okay, now 0 over q by the equivalency of fractions is 0 over 1, that is the rational 0. Similarly, for any non-zero rational number, the multiplicative inverse is basically the fraction flipped. So if I flip the fraction, then this will be q over p. You multiply that with p over q and you will get 1 over 1, again equivalency of fractions, and that is the rational one. Distributivity. Now this is also pretty easy to prove. All you need to do is evaluate this addition first, then use the multiplication definition, and then you can just split the fractions again. You can split this into two fractions, that is p by q times r by s, this term, and p by q times u by v, which is basically this thing distributed. So this concludes that q, that is the set of rationals under the operation of plus and multiplication, is a field. Okay, so in the next video I'll start with vector spaces. This is it. I have shown you a case study on how we can prove that something is a field. I hope that if you encounter anything else and you have to prove it as a field, I hope you will remember all these techniques, and mainly just remember just memorize the definition of field, all the 6 rules that govern whether something is a field or not. Alright, thank you. Stay tuned for the next lecture. I'll see you then.